Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today's session we would like to talk about something totally new. Okay, so to be more precise, what we're going to talk about is a new type of field as shown here, known as magnetostatic field. Okay, that should be our main objective. So we're going to learn something totally different from what we have learned before. So let's go on now. So we're going to talk about new field known as magnetostatic field. Okay, that should be our concern. So as what we're going to see later on, the approach of learning this new field will be similar from what we have encountered when we talk about electrostatic field. In terms of approach, in terms of flow of the information, going to be exactly the same. You will see what it actually means, but the only difference going to be the specific detail as what we will explain later on. Okay, so it will be nothing new, going to be the same as electrostatic in terms of approach, but only the field going to be slightly different. Okay, for those who have textbook, you can read about this new field mentioned in Sadiku textbook. Okay, so starting from page number 289. Okay, that should be the first page talking about a magnetostatic. So what is magnetostatic field? Okay, magnetostatic can be divided into two words here, where the magneto indicate to us we going to deal with only magnetic field. As what you have experienced when we discuss about electrostatic, the only field that we need to consider is electric field. So for magnetostatic, the similar concept is applied, which is magneto indicate to us the only field that we're going to deal throughout this particular field is known as magnetic field. And magnetic field can be divided into two types. Okay, we will represent the first type of field known as magnetic field intensity. Okay, and symbol to represent magnetic field intensity will be H. So it's similar to electric field intensity. And the second type of field that we can represent known as magnetic field density. Okay, it's similar to electric field density. So now the symbol for magnetic field density will be known as symbol vector B. Okay, so that's how we represent the field, the magnetic field. And from the name of magnetostatic, the static is here having the meaning similar to what we have interpreted in electrostatic, meaning that the field is independent of time. Okay, so whatever the field that we're going to represent, for example, the H going to be as a function of X, Y, and Z only. If we are using which coordinate system? Cartesian coordinate system. And if you are using a cylindrical coordinate system, the H is only a function of R, phi, and Z. So no T in our model of mathematics. Because why? for magnetostatic, the magnetic field is independent of time. Okay, so now let's go to the source now. How we actually generate this field. Okay, so the source. So for electrostatic, we have defined the source for electrostatic will be stationary charge. Okay, so for magnetostatic, the source will have first common behavior is moving charges. Okay, so that should be the first common behavior of all the source in the magnetostatic. They should be charge that move, and we can represent this idea mathematically as vector J. Okay, J is known as current density, and one equation that we have seen before, the J can be represented by charge that move or moving charge. So that should be the basic pattern of the source for magnetostatic field, moving charge. So now we have to go in more detail. How about the U value? So the second characteristic should be U is constant. Meaning that the charge is moving with constant value. The acceleration will be equal to 0. No acceleration. So example wise, we can assume source for magnetostatic can be known as DC current. This is how we represent source for magnetostatic. If the charge is moving with varying speed, meaning that there is acceleration and deceleration, that's going to be a source for the third model of field that we're going to learn later on, which is known as electromagnetic field. Okay, so now you can see the same charge. If it remains stationary, it's going to emit electric static field. The same charge is moving but with constant speed, it's going to generate magnetic static field. And the same charge, when you apply acceleration to it, or it contains acceleration, or the velocity is varying, so it's going to generate electromagnetic field. But our concern at this stage is going to be the charge is moving with constant speed. And we're going to develop model for it. Okay, so the model that we're going to represent, so I mean the source can be represented in terms of model. Okay, the first type of source that we're going to represent in terms of model, we're going to name it as filamentary current. Filamentary current. Or in other words, line current. Okay, so that should be the first model of source for magnetostatic. So let's say we have a diagram to represent this particular model. So let's assume our line current having these shapes. Okay, so this is our line current, and you can see it's quite similar to our line charge that we have seen before in terms of diagram. So, but now what contained in this line will be current. I'm going to define now the current as symbol I. Okay, so now we have a line pattern, and in the pattern contains a current, and let's assume the current having magnitude I. Okay, so as what we have done in our electrostatic model, yes, we have to take sample. Okay, now this is our sample. Sample can be taken at any location on our source, and we call this sample, okay, as filamentary current element. Filamentary current element. Okay, so in other words, is our sample. Okay, so we have represent mathematical model to it. So what going to be the equation to represent our sample for a filamentary current? So it's going to be first, what we can see passing through this sample will be the magnitude of current. Yes, that should be our I. Okay, and second properties that we can see is that is associated with the sample going to be the length sample, and since the sample is going to be very small, so we're going to represent the length as vector dr. So now you can see the vector is on the length parameter, not on the I, because I, as what we have defined in our previous lecture, is going to be in scalar form. So not going to be in vector. For current to be in vector, should be in the symbol J. Okay, since we are represent the current here as I, so it's going to be in terms of scalar format or scalar term. Okay, so let's talk about the unit. So the unit for our sample going to be ampere meter. Okay, so that should be the general unit for all the sample of source for magnetostatic, going to be ampere meter. Okay, hope you can see this idea. Okay, let's continue. So we're going to go to the second type of source for magnetostatic. Yes, it's going to be surface current. As you can see now, in terms of flow, it's quite similar to what we have seen in electrostatic domain. Because in our electrostatic, the source known as line charge, and then we continue with the surface charge. So what you can see there is reappearing now. So first filamentary current, second surface current. So I can presume you are guessing the model for my surface current going to be quite the same as my surface charge. Good. So I'm going to draw about the same shape that we have drawn before. Okay, that should be my surface current model. Okay, so now we're going to represent the current. Okay, the current, since the charge can move in any direction on the surface, so we have to represent the current with symbol J. It's not appropriate to represent the current with symbol I, because now direction of the charge movement is critical. So therefore I'm going to represent my current as symbol J. But since the current is only appear on the surface of the structure, the current going to be very thin. We're going to define that to be surface current density. Okay, that's why we put the subscript S there as representation for surface current density. So this to differentiate with our previous current known as J current. That should be logical to be for our third model later on. For second model, since it's only flow on the surface of the structure, we define that to be the current to be known as surface current density. Okay, so we have to take sample. I'm going to take sample now. So this is my sample. So now the sample now should have mathematical equation representing that sample. So how are we going to represent this sample? Yes, first the current that passing through the sample, what we see, good, the surface current density. So since it's a vector, please represent it as a vector, the surface current density. How about the second parameter? Yes, the area of our sample. So that should be defined as as ds. Okay, the vector only applicable on the current density, whereby the ds must be in scalar form. And the unit for this particular sample still having ampere meter representation. Okay, so as you can see now, what should be the unit of the surface current density. So the unit for surface current density should be, what is it? Good. Ampere per meter. Okay, and the unit for area going to be meter squared. Therefore, the final unit for sample must be ampere meter, which is similar to what we have shown for the sample for filament current. Okay, that's very crucial. Later on, when we solve problem, the unit will help us defining how we're going to assume the model of our sample or our problem. Okay, can we continue to the last sample here? Good, so I'm going to go to the third model that we're going to represent the source. Okay, you can guess now, it's going to be volume current. Okay, volume current. And then let's draw our structure, usually a cylinder. Okay, that should be the typical shape of our volume current. So now what's going to happen, current will flow inside the volume of this structure, and the symbol for the current going to be J. And you can see now J and JS, they are totally different entity, whereby JS, surface current density, J known as volume current density or current density. Yeah? Okay. How we take sample? Okay, we're going to take sample. We call the sample known as volume current element. So the mathematics should be vector J dV. Because our sample now should be in terms of box, three-dimensional. Okay, so that should be our third model. The unit for this sample still ampere meter. The unit for J going to be ampere per meter squared, whereby the unit for volume, as what we have seen before, will be meter cube. Okay, so that should be three typical source that generate field known as magnetostatic field. First one is filamentary current, second surface current, third volume current. It's quite similar to what we have seen before in electrostatic, line charge, surface charge, and volume charge. Okay, so that should be our source for magnetostatic. Okay, so now I'm going to continue my lecture. Okay, so what we're going to do now, we're going to talk about the link between the source and the field. That's what we're going to discuss now. Okay, so what we're going to talk now, the relationship between the source, okay, and the field. Okay, that should be the concern that we're going to address, how we relate, how we develop the relationship between the field and the source. Let's recall the first type of field that we have seen, electrostatic. I'm going to represent my electrostatic with red color. Okay, so that should be our, this is like revision here. So the source for electrostatic, we represent general representation as rho V, okay, and then the field that we represent known as electric field intensity vector E. Okay, so these two parameters can be linked together with a law. We define it to be Coulomb's law. Correct? So that should be the approach. And then Coulomb's law state, based on our discussion, dE vector going to be equal to the sample. I'm going to put sample now. Okay, and then going to be multiplied with the unit vector. And I'm going to divide everything with 4 pi epsilon r squared. Is it correct? Okay, that should be our Coulomb's law model that we have seen, and we have done a lot of examples using these laws. So now let's talk about the current field, magnetostatic field. Okay, you have to always remind yourself the way learning magnetostatic is similar to the approach that we have done when we talk about electrostatic. Okay, so it's going to be the same. So now, let's represent our general current source. For electrostatic, volume charge. Therefore, for magnetostatic, it's going to be volume current. So it should be J, vector now, correct? And then we know the field for magnetostatic, which is similar to electrostatic field, E will be our H. Okay? E, electric field intensity. H going to be magnetic field intensity. Okay, now we're going to link together these parameters, and then what we're going to, the laws that we're going to use here in order to develop or to determine magnetic field from the source going to be Biot-Savart law. Okay, and you can guess from the model, Biot-Savart in terms of equation going to be similar to Coulomb's law. Okay, so again, in terms of equation, Biot-Savart law is going to be similar to Coulomb's law. So I'm going to copy now, but slight adjustment, dH going to be the magnetic field similar to dE, equal to, and then sample, and then AR over 4 pi r squared. Okay, so that should be the first difference that we can observe. There's no epsilon. Why? Epsilon here, as what we have learned before, how the material respond to which field? Yes, electric field. Remember when we talk about dielectric under static conditions? So material respond to electric field. So epsilon is parameter that determine how the given material respond to electric field only. Okay, so this way you have to refer to material atau under static conditions. So I'm just going to put note here, material under static conditions, and the static field is specifically referred to electric field. So since we are talking about magnetic field, logically, there's going to be no epsilon in our Biot-Savart law. Okay, you have to see that pattern because epsilon only applicable for electric field. So in magnetic field, epsilon will not be involved in the equation. Okay, that should be the first difference between Coulomb's law and Biot-Savart law. And the second difference going to be, there's going to be a cross product here, whereby for Coulomb's law, just simple multiplication, scalar multiply with vector. But for Biot-Savart, since the sample here is a vector and AR is a vector, so we have to use proper vector multiplication. So to be more specific here, should be cross product, not dot product. Why? Because H in terms of what? Vector or scalar? Yes, vector. So for a vector, multiply a vector to produce a vector, we must use the mathematical term known as cross product. Okay, that should be the second difference between Biot-Savart and Coulomb's law. So we're going to rewrite the equation in more detail now. It's going to be equal to, so since we are dealing with volume current, remember vector J dV cross AR divide with 4 pi R squared. Okay, so that should be the equation. So let's say if the current now change into filament current, so this term just need to be changed into I dl vector. And if the sample now, or if the problem based on surface current, you just need to change this term with the model mathematic JS vector ds. Okay, apart from that, the process of solving the mathematics going to be the same for all the three different model of source of magnetostatic. Okay, so that should be what we call it now, the method to determine field, which is to be specific magnetic field from the current source. Okay, so what I'm going to do, I'm going to do example. So since example here, I want to make the learning process is something that nothing new. So my example one is going to be the same as our example one in Coulomb's law. Okay, so in terms of shape of the source, example one for Biot-Savart law going to be same pattern as our example one in Coulomb's law. I think you can guess how what it's going to be. Okay, so let's do that now. See, let's say you have a source now, as shown here. Okay, this is our source. Okay, the source is along the z-axis. Okay, this is our x-axis, y-axis, and z-axis. And what should be the shape of our source on the z-axis, which is similar to the one that we have seen in our electrostatic example 1 sample? Yes, a line structure. Good. So I'm going to redraw that. The only difference here, we're going to have a current I. Okay, so I going to be the current flow in the line structure, whereby in our electrostatic, we represent that to be rho L, line charge density. And what should be the limit of my line structure from A up to B? As you can see, exactly the same as what we represent before in line charge problem. So let's say what should be the question now. Okay, find H. Okay, that should be the question. Find magnetic field due to this particular source. Okay, so now how we solve it? Remember, approach similar to Coulomb's law. Good. We're going to select appropriate coordinate system. Good. Cylindrical coordinate system should be the coordinate that we're going to use here. Then what should be the second step? Yes, location of our field. I'm going to define the location to be, let's make it to be here. It's quite similar to the one that we select for electric field. Okay, this is where I'm going to determine my magnetic field H due to the line current. So I'm going to relate the location now with our first step that we did just now. We are selecting cylindrical coordinate system. I'm going to link it to our cylindrical coordinate system. Yeah? So this should be 90 degrees. What should be the distance here? R. Yeah? Radius. And then I'm going to redraw this. So this angle going to be phi. Okay, and the height going to be z. Okay, so now I'm representing the parameter associated with the location of where I'm going to determine the magnetic field using the selected coordinate system, which in this case R, phi, and z. Okay, so that should be my second step. For the third step, I'm going to take sample. So I'm going to take it here. That's what we have done. It can be anywhere on the line current. So I'm choosing this position because it's exactly the same position I choose when we solve a problem for line charge. And then what should be the length here, since this position is not fixed, I'm going to put it Z prime. Okay, so this is my sample. And then what I'm going to do for the fourth step, I'm going to link the sample to where I'm going to determine my field. So that should be my vector R. Okay, now I'm going to do what? I'm going to extract information from this diagram to be substituted into my general Biot-Savart equations. So using Biot-Savart, we're going to write it here using Biot-Savart law. So we can know that the DH here going to be I dl cross AR divided with 4 pi R squared. That should be our general Biot-Savart, where we're going to say I dl going to be equal to I dz prime in z directions. Yeah, because why? Because I flowing upward. Let's say in the problem I is flowing downward, so the z here should be represented with negative z. Okay, and then what should be the next two? The r, vector r also from the diagram again, please. So what should be my vector r? Yeah, should be the horizontal component minus z prime minus z directions. Okay, so that should be the step you should use. Now, therefore, what we're going to have now, our DH going to be equal to I dz prime z directions, okay, cross with what should be now r vector minus z prime minus z negative z directions, divide everything with 4 pi, okay, and that should be r square plus z prime minus z square power of 3 over 2. That should be the final equation after substitution from the above parameter extracted from our diagram. Okay, let's continue our mathematics. So we have to do cross product now. What should be the solution of z term cross with r term? Z unit vector cross with r unit vector. What should be the solutions? Okay, so for those who can't remember, you can use my step here, how I do it. Okay, I'm going to represent my unit vector as this simple diagram. For cylindrical coordinate, this should be given in terms of r unit vector. So this should be phi unit vector, z unit vector. So now I'm doing the cross product z cross r. Using my right hand rule, I'm moving from z to r. So my hand moving from z to r. My thumb is showing what now? Yes, phi unit vector. So that should be the solution for z cross r, going to be the phi. So I put it there, phi. Okay, so again, z cross z will end with 0. So no, because cross product, remember, when the unit vector is parallel, the angle is 0 degree and sine 0 degree will be 0. So now our solution here going to be equal to, okay, I r dz prime, okay, divide everything with 4 pi r square plus z prime minus z power of 3 over 2, and don't forget about the direction. So be which directions? Yes, good, phi directions. Okay, so I r dz prime, good, and then phi direction, divide everything with whatever appear at this particular part of the mathematics. Yeah? So now let's continue. I have to solve the mathematics now. Okay, so now we have to do integration now. Yeah? So now let's continue. So H now will be equal to, I'm going to take all the constant out, so going to be I R over 4 pi. That should be my constant. Integrate, and then going to be, okay, phi, okay, don't forget we're going to take the phi as well. Okay, dz prime, divide everything with r square plus z prime minus z square 3 over 2. Okay, that should be the integration. From where to where the limit of our integration? Yes, refer to the diagram again. And then we can see the limit is from A and at B, based on our model of current. So I'm using table now. So you can refer to table, page number, I presume, 844. So based on the textbook, refer to page 844. So you can see that. So we're going to just take the solution from that table. So you're going to be equal to phi I R over 4 pi. Okay, I'm going to show the output of that table. Going to be z prime minus z divide with r square, square root of r square plus z prime minus z square, and then from where? A to B. Okay, that should be from the table. Nothing extraordinary, yeah? Rather than using the complicated mathematics method, substitution, etc. I'm going to, in this case, just using table as our method to solve the integrations. So when you do that, what you're going to have now is going to be phi I divide with 4 pi r. Do we agree on that? Because this r and this r square can be cancelled out. Yeah? So therefore that should be 1, and then I'm going to substitute now. First b should be b minus z, divide everything with r square plus b minus z square. That for the first substitution for the limit, minus the second substitution will be a minus z over r square plus a minus z square. Okay, close bracket, and the unit should be ampere per meter. So that should be the solution of our magnetic field that generated by our line charge as shown here. Yeah? So therefore, I'm sure you have seen the same process being done when we solve electric field generated by line charge, and then the equation that we obtain in Coulomb's law is much more complicated than what we've seen here. Alhamdulillah, we're having easier solutions. So what's going to be the logical step we're going to do for this approach then? Okay, yes, as what we have done in Coulomb's law, we're going to represent this solution in terms of graphical form. Yeah, remember that approach? Okay, I'm going to do that here. So let's do that now. So I'm going to redraw the problem. Okay, redraw the problem in terms of 2D now. Yeah. Okay, 2D. So I'm going to say now this is my line current flowing upward, I from A to B. Okay, then I represent my H location to be here, and then the distance from the sample to H location for this position 90 degrees, I'm given as R. Okay, and then I'm going to represent angle now, and then where the current starts, I'm going to define this angle as what we have done in electrostatic, alpha 1, and then where the current is ending, we're going to represent the upper angle as alpha 2. Exactly the same as what we have done before, nothing new. So everything the same. Then we're going to give dimensions. Okay, this is going to be known as length, B minus Z, correct? For this side, this particular diagram going to have length given as Z minus A. And based on theorem Pythagoras, this side of the triangle going to be equal to R square plus B minus Z square. So whereby this side going to be having length as R square plus Z minus A square. Okay, and from our previous solution, we have know that the H here, okay, is given as phi directions. I divide with 4 pi R B minus Z over square root of R square plus B minus Z square minus A minus Z over square root of R square plus A minus Z square. Okay, that should be taken from our solution before. Okay, so there you are. Now we're going to rearrange the solution based on the triangle. So let's compare equation with the diagram. So I'm going to focus for the red box part first. So I can see B minus Z is actually represented by this side of the triangle, and R square plus B minus Z square square root going to be represented by this part of the triangle. I know based on trigonal, when you have this side divided by this length, this can be known as sine, which angle? Yes, alpha 2, because this is what the angle referred to. When you have this side divided by this side, going to be sine alpha 2. Yeah? Okay, let's repeat for the second part now. Okay, so I'm going to see this term now. So this should be our concern now to simplification process here. Okay, what I see from the triangle, the symbol here is given by Z minus A, whereby what we have in the equation A minus Z. So we have to make it the same. So what we have to do, we have to manipulate the mathematics. It's going to be plus, minus, plus. Okay, so therefore we're going to conclude this going to be known as sine alpha 1. Because this term does not matter, because when you have square, so when negative value will end with positive value as well. So this is not very significant. Only this part of the mathematics is very critical. They must be the same. So therefore, you have to manipulate the mathematics by changing negative or minus to become plus here. Okay, so with triangle, with the diagram, now our H must be given as in terms of phi. I divide with 4 pi R sine alpha 2 plus sine alpha 1. So that should be the second method that we can use to represent magnetic field due to finite line current. The first method using this lengthy equation. The second method using slightly shorter version, but this equation must come together with this diagram. Okay, so let's extend this problem slightly different now. So let's say example 2. Okay, find H due to infinite line current. Okay, that should be a general equation. So now we changing our question from we are still dealing with line current, but before what we dealt with known as finite line current, where there's a limit to it from A to B. But for this problem, our line current now is becoming infinite. So how are we going to solve this problem? Good, we're going to use the above equation. Which one? This one. Okay, using equation, so I'm going to put equation what here? Equation correct, okay? But for infinite, okay, where A, or let's say B first, B now tends to move to where? Infinity. That's what we define by infinite. The B is not located here, it's going to be very far away. Let's go to be infinite. So what happened to the angle when the B moved to infinite? Alpha 2 now will become equal to what? Good, 90 degrees. And again, if A now is going to be representing infinite line current, going to be located where? Minus infinity. Therefore, what happened to angle alpha 1? Yes, equal to again 90 degrees. So therefore, what we're going to have here, the H is equal to phi I over 2 pi r ampere per meter. Remember, for E due to infinite line charge, yes, I divided by rho L divided by 2 pi r, if not mistaken. That's what we have solved before. So now for this case, it's I divided by 2 pi. It's quite similar if we compare to the problem of infinite line charge. So this is something that we always need to remember, because by remembering this solution, we're going to make our problem solving becoming much simpler. When we assume infinite line current need to be solved, straight away we're going to use this equation as our starting point, because we don't have to prove it if you've not been asked to prove it. Okay, that should be done. So can we do one more example? Good. Okay, I'm going to do example 3. Okay, example 3. This is our last example for today's lecture. Example 3. Okay, something similar again. So what should be something that you've seen before when we solve line charge? Good, I think you can still remember. So what we have circular ring, remember, located where? On the XY plane. And the axis of the ring is coinciding with the Z-axis. So that should be the one that we're going to solve here. So X, Y, Z. And then now, since we are dealing with current, so now the current should be presented by I. And then the radius, something similar than before. Yes, A. Okay, so find H along the Z-axis. That should be our problem here. Find H along the Z-axis. Yeah? So I'm sure it's similar. If you see the idea, similar when we solve Coulomb's law before. Okay, so how we continue? First, coordinates. Good. Cylindrical. Second, where should be our H location? Yes, up here. Why? Along the Z-axis. Okay, so I'm going to represent the height as Z, because it's not fixed. Okay, This point can be moved along the z-axis, therefore I'm giving the variable to be z. Okay, then the steps next, after that, going to be taking sample. I'm going to take my sample here. Okay, and then the following step going to be joining the sample to our H location, and that should be our R vector. Okay, so standard method. So okay, now should be what? Okay, using Biot Savart. So what should be our general equation here? Yes, dH going to be equal to I dl cross AR, divide everything with 4 pi r squared. Right? Good. Now we have to determine I dl unit vector r from where? Good, from the diagram. Yeah? So I'm going to sit from the diagram. Okay, what we can observe, I dl should be equal to what? The sample here. Okay, I still remain I because we see I is the magnitude of the current. Somehow if the problem give here 2I, so we have to put 2I here. And then how about the dl? So the dl here based on our cylindrical coordinate vector. So this segment is changing in terms of phi, correct? Because it's angle phi. Okay, so the radius fixed and the z fixed. So therefore, for dl, where the phi, where phi is changing, is going to be given as a d phi. In which direction? Phi direction. Yeah? Because moving in this direction by default positive phi, whereby if the current flow in opposite direction, shown here is going to be negative phi. Yeah? So therefore done. And the second important parameter need to be defined from the diagram is R. Okay, R should be equal to negative AR plus ZZ. Okay, that should be our vector R. Yeah? So therefore what we're going to have here, our DH now going to be equal to I A D phi phi cross with negative AR plus ZZ. Everything I'm going to divide with 4 pi A squared plus Z squared power of what? 3 over 2. Agree? Yes. Now let's continue solving the mathematics. How? First by cross product phi with negative R. So what should be the solution of this cross product? Phi with negative R. Okay, so it should be phi negative R. That's good. Z directions. And the second part now, phi cross with the Z now. Okay, phi cross the Z. What should be? Yes, should be R. Okay, correct. Okay, phi cross Z should be R. And then phi cross negative R should be Z. Okay. So now what we have here, two components vector should be I A d phi over 4 pi A squared plus Z squared power of 3 over 2, and then the solution of multiplication now becoming AZ plus ZR. Okay. Good. So now let's continue. So I have to solve for H now. Okay, finally H should be equal to what now? So in order to simplify my integration, I'm going to use graphical diagram now. So I'm going to do it. How? So I'm going to take sample on both sides of my ring. So our first sample is located here, okay? And I'm going to take my second sample. So if you continue this sample position passing through the origin, moving to the other side, I'm going to have another sample here. So how many samples I have in my diagram now? 2 samples, one black color, another one blue color, okay? So let's draw this problem in 2D, two-dimensional. So what I'm going to have now, so this is the dotted line. Okay, dotted line represent what? This dotted line. And then I'm going to have my z-axis at the center of this dotted line. So that should be our z-axis, correct? Okay. Now, on the right, I'm going to sample. Which color of our sample on the right? Yes, black color. On the left, the sample is what color then? On the left, the sample is blue color. So I'm going to draw it. Distance-wise, the same. Okay, distance should be A. Here also should be A. What is the behavior of the current on the right-hand side? Okay, as you can see in our model, the current actually flow in the field directions. So in 2D representation, okay, for the black sample, the current is assumed to be going into the paper, correct? Because it's moving away here, so going into, whereby the current on the right, on the left, as you can see here, is coming toward us, so it's coming out from the paper. That should be our typical sample current flow. Black sample current going into the paper. Okay, blue sample current coming out from the paper. So if I have this particular behavior, I can see somehow there are 2 line current. Because I don't see this diagram, I just see this diagram on the right. I can assume the right hand side of my current going to be line current going into my paper, whereby the left hand side of my current is represented by line current coming out from the paper. So I want to determine H here. Okay, based on the previous problem that we solved up here, okay, we can use this idea now. So the current going to produce field magnetic in terms of the field directions, meaning that in terms of these directions, okay, circulating directions. Okay, so now how about the direction now? If it's coming going into, so therefore the direction going to be tangent. So that should be our black field DH. Okay, so now, so how I know that? Because it's going to make 90 degrees to the radius of this circular loop. So this is our magnetic field. But now what we want to determine the magnetic field due to the sample black color located here. So for the direction can be represented in terms of tangent. And we can see this tangent can be split into 2. One going to be DHR. Another one we're going to call it to be what here? Yes, DHZ based on our cylindrical coordinate. And when we compare this diagram to our solution, yes, we can see the similarity. Okay, there's a R term, yeah, that's representing this particular component of the field, and there's a Z term here, is represented by this component part of it. So now DH actually consists of R term plus Z term, and our DH actually in terms of equation consists of R term plus Z term. Okay, that should be our field generated by sample black color. How about the sample blue color? Yes, it's going to repeat the same thing. It's going to produce its own field, also a circular shapes because of the field. And then now, how about the directions coming out? Therefore, the direction of the field must be in this direction, DH for the blue sample. And then we know it's 90 degrees, and we can define it to be horizontal component and vertical component. Okay, horizontal DHR, vertical DHZ. So now, when I integrate, okay, now we're going to integrate now H. equal to phi I a squared, okay, over 4 pi a squared here plus z squared 3 over 2. So which term I'm going to take into consideration after the integration or in the integration? Because I know that integration meaning that I'm summing the black field with the blue field. So when I sum this field together, I can see from the diagram the component of R, since they are opposing each other, they're going to be cancelled out after the integration. And we're going to end with only which component? Yes, the one that in the same direction, Z component. Okay, therefore I'm going to take the Z1, so it's A squared, and then now this term now change into Z directions. Okay, and then I'm going to integrate now d phi from where to where? 0 to 2 pi. Why? Because it's a complete ring. And my final solution going to be equal to Z directions I a squared over, okay, 2 pi and 4 pi. Yes, going to end with 2 a squared plus z squared power of 3 over 2 ampere per meter. Alhamdulillah, we managed to solve the problem. So therefore, that should be a typical method we can use when we are using Biot-Savart law. As a conclusion, the method is similar to what we have done in Coulomb's law. So therefore, learning magnetostatic is slightly easier because it's repeating what we have learned in the world of electrostatic. So therefore, with that, I'd like to say thank you very much for your attention. So inshallah, we're going to see each other in my next video. Assalamu alaikum wa rahmatullahi wa barakatuh.